Right. So as I told you in the last class that in non-ideal solution, the calculated total pressure, calculated means using Raoult's law. Using Raoult's law, the calculated total pressure and the experimentally measured total pressure. Okay, calculated and experimental pressures, these are not equal. If the two are not equal, we call the solution as non-ideal solution. Okay, that's the first point you should keep in mind. Okay, calculated total pressure and observed pressure are not equal. Then if they are not equal, then two possibilities arises. Two possibility. What are they? The experimental pressure may be greater than the calculated pressure, or the experimental pressure may be less than the calculated. If observed pressure or experimental pressure, if it is greater than calculated pressure, we call those solutions as non-ideal solutions showing positive deviation. If the observed pressure or the experimental pressure, if it is less than the total calculated pressure, then we call those solutions as non-ideal solutions showing negative deviation. Okay, so we have two types, right? And I also told you how to calculate the total pressure using Raoult's law. Yes, if you want to calculate total pressure, okay, using Raoult's law, this is the formula we follow. We use, okay, P naught A into XA plus P naught B into XB, where P naught A is the vapor pressure of pure liquid A, P naught B is the vapor pressure of pure liquid B, XA and XB are mole fractions of A and B in the liquid phase. Okay, yeah, so keep this in mind. Now first we'll start with the non-ideal solution showing positive deviation. Okay, right. Yeah, everyone turn on your camera. Yes, turn on your camera. Okay. Now, so non-ideal solution, non-ideal solution showing positive deviation. Solution showing positive deviation. Positive deviation from ideal solution, that's the meaning. Non-ideal solution showing positive deviation from ideal solution. Okay. Now, when we'll get positive deviation, what is meant by this? Suppose I'll take two liquids A and B, liquid A, and I'll take liquid B. Okay, so in liquid A we have attraction between AA molecules. In liquid B we have attraction between BB molecules. Okay, now if I mix the two, I'll get a solution containing A and B. Okay, in solution you'll be having attraction between A, B and molecules. Okay, in solution we have new attraction between A and B molecules. Okay, now if the attraction is weak, right, if the force of attraction between AB, right, if it is less than the force of attraction between AA or BB, anyone, at least anyone. If the force of attraction between AB, if it is less than the force of attraction between AA or BB, then what will happen? Listen, if force of attraction is weak in the liquid phase, then the molecule will easily escape from the liquid phase and occupy the empty space that is available. That is become vapor. So you will get more vapor. Okay, so you will get positive deviation. Simple. I repeat, what I am trying to say here is, listen, if the force of attraction between A and B in the liquid phase is weak, then the molecule will escape from the liquid phase and go to the vapor state. So now more molecule will go to vapor state. Therefore, the experimental vapor pressure or observed vapor pressure will be greater than the calculated vapor pressure. So what will happen? So in this case, the observed vapor pressure, okay, observed total vapor pressure, also called experimental pressure, will be greater than the calculated total pressure. This is calculated. Why it is greater? Why the observed pressure is greater? Because the force of attraction between AB in the liquid phase is weak. Okay, if the force of attraction is weak, then molecule will go to the vapor state. So more molecule will come to vapor state. Therefore, vapor pressure increases. Okay, so observed vapor pressure will be more than the calculated vapor pressure. Right? Then we call this type of solutions as solution showing positive deviation from Raoult's law or positive deviation from ideal solution. Okay, so keep this in mind when we can say a non-ideal solution showing positive deviation. Right? If the force of attraction between AB molecules is less than force of attraction between AA or BB, then the observed pressure become more compared to the calculated total pressure. In this case, we call this type of solutions as solution showing positive deviation. Right? Then in non-ideal solution, the second point that you should keep in mind is, in non-ideal solution, see, force of attraction is weak. Whenever force of attraction weak, what will happen? Right? Volume will increase. See, what I am trying to say is, listen, assume that the volume of liquid A is VA. So VA is the volume of pure liquid A. VB is the volume of pure liquid B. Okay, so what is the total volume before mixing? Total volume before mixing is VA plus VB. This is total volume before mixing. Right? Now, if I mix the two, I will get volume of the solution. Okay? If the force of attraction, see here, if the force of attraction is weak, okay, less than AA or less than BB, that means it is weak. If the force of attraction is weak, then solution volume become larger. Solution volume become larger compared to the sum of these. Okay, so what is meant by that? In solution showing positive deviation, volume of the solution is greater than the sum of volume of the pure liquids A and B. Okay, so this is before mixing total volume. This is total volume after mixing. Total volume after mixing is greater than the total volume before mixing. Therefore, if you calculate delta V mixing, what is delta V mixing? Change in volume due to mixing. Okay, delta V mixing is equal to, what is delta V mixing? Simple, volume of the solution, this is after mixing, total volume after mixing, minus total volume before mixing, VA plus VB. So I have told you volume of the solution is greater than the sum of these two. Therefore, larger value minus smaller value, if you subtract, you will get the answer as positive. So you'll get positive value. Okay, students, is this clear? Any doubt here? So for solution showing positive deviation, delta V mixing is positive. Remember, for solution showing positive deviation, delta V mixing is positive. Why? Because force of attraction between AB is weak. Therefore, the solution occupy more volume compared to the total volume of liquid A and liquid B. Okay? Then, what about delta H mixing? Next point. What about delta H mixing? Students, this is very important. Whenever force of attraction between AB, okay, if it is weak compared to or less compared to force of attraction between AA or BB, then what will happen is that see here, that means AA attraction is stronger or BB attractions are stronger. If you mix them, the force of attractions, okay, is reduced. To reduce force of attraction between AA as well as BB, right? Or I can say in the other way. Here the force of attraction is weak, right? Whenever force of attraction is weak, right, you must supply energy. Okay, so what is meant by that? What I am trying to say is, you take liquid A and you take liquid B, okay, you mix them, you will get a solution. You get a solution of A and B. Solution of A and B. In this case, you must supply heat. Okay, you must supply heat, or heat is absorbed. Why heat is absorbed? Because to reduce the force of attraction between AA and the force of attraction between BB, right? So that you will get weak forces in A and B. To get weak forces between A and B, you need to supply heat, right? Whenever forces of attraction decreases, you must supply heat. So, or I can say in the other way, if force of attraction between AB is less, which means you have to supply heat, or the heat is absorbed while forming the solution. Okay, therefore this process is an endothermic process. It's an endothermic process. Heat is absorbed, right? Which means delta H mixing should be positive. Endothermic means it should be positive. Okay. Why positive? Because forces of attraction decreases. Whenever forces of attraction decreases on mixing two liquids, okay, it means this during this process heat is absorbed from the surrounding. Okay, whenever heat is absorbed, we call the process as endothermic process. Endothermic means delta H is positive. Okay, then the next one, this is delta H mixing. Then what about delta S mixing? Delta S mixing. What about delta S mixing? Right. Before that, let me take delta G mixing. I'll come here, then I'll come back to here. Delta G mixing. I'll finish off delta G mixing so that you can easily understand this. What is delta G mixing? Listen, whenever you mix two liquid and if you form a solution, if solution is formed by just mixing A and B, we call the process as spontaneous. You take liquid A and liquid B, just mix them. By just mixing, if you get a solution, right, it is called a spontaneous process. Since the process is spontaneous, delta G mixing should be negative. Why negative? Because solution is formed. Okay, Solution is formed spontaneously. We didn't do anything. We are just mixing A and B. You'll get a solution, right? By just mixing A and B, if you get a solution without doing any external work, we call the process a spontaneous process. Okay, for spontaneous process, delta G mixing is negative. Okay, now I'll go here. So for solution showing positive deviation, delta G mixing is negative. Keep this in mind. Now I'll go to this one, delta S mixing. You know very well, delta G mixing equal to delta H mixing minus T into delta S mixing. Students, observe this carefully. Delta G mixing should be negative, that we know. Then only the process is spontaneous. Okay, and delta H mixing, I have told you, delta H mixing is positive, right? See here, we have already discussed delta H mixing is positive. Minus temperature is always positive, that you know, because we give temperature always in Kelvin. Then what should be the sign of delta S mixing, so that I'll get negative? Okay, see, left hand side is negative, therefore right hand side should also be negative. To get negative value, what should be the sign of delta S mixing? Can anyone fix this?
Positive, sir.
It should be positive, correct? Why? If it is positive, positive into positive is positive, but here we have negative sign, so you'll get total negative here. So negative minus positive, assume that this value is larger. Because you are multiplying these two. Okay, so this value will be generally quite larger in this case. Since it is larger, okay, compared to this value, therefore delta S mixing should be positive. Right here, it should be positive. Okay, and here you got another information by working out this. What is the information? Delta H mixing and T into delta S mixing. Students, observe this carefully. T into delta S mixing is positive, correct? Because temperature is positive, delta X mixing also positive, we found that. Okay, if these two are positive, positive into positive is positive, delta H mixing also positive, but in these two, if this is greater, if T into delta S mixing is greater than delta H mixing, we will get solution with the positive deviation. Note down, very important. For solution showing positive deviation, if delta H mixing is positive, T into delta S mixing also positive, but among the two, which value is greater? The magnitude, right? T into delta S, this magnitude is greater. It is supposed to be greater. Then only you will get delta G negative. Is it correct? So keep this in mind, very, very important. For solution showing positive deviation, T into delta S mixing should be greater than delta H mixing, right? Yeah. So I have given the characteristics of the solution, non-ideal solution showing positive deviation. Now I'll give examples. Yeah, before going to see, okay, yeah, we'll see examples. Once I finish examples, I'll give you the summary. Examples. Students, to identify, this is actually very important part in in the competitive examinations. Okay, they'll give two liquids and they will ask you to find whether the two liquids form ideal solution or non-ideal solution showing positive deviation or non-ideal solution showing negative deviation. Okay, to identify this, what we have to do, among the two liquid, which liquid has stronger force of attraction, that you have to see. Okay, see, they'll give two liquids, liquid A and liquid B. What you have to do, see the two liquids, identify in which liquid stronger force of attraction exists, stronger force. Okay, then what you have to do is mix the two. After mixing, see the force of attraction between A and B, right? Then you can easily say that which solution, whether the solution will give positive deviation or negative deviation, or it is simply ideal solution. Okay, yeah. So for this, what is required is you must know which solution or which force of attraction is stronger. You know very well, ion-ion attraction, students observe carefully, ion-ion attraction is very strong compared to all other attractions in general. Ion-ion attraction is very strong, right? Then ion dipole attraction, ion dipole, then hydrogen bonding attraction, hydrogen bonding, then dipole-dipole attraction, dipole-dipole attraction. Okay, then we have what is called attraction between non-polar molecules. Okay, attraction between non-polar molecules, it is actually called London forces, right? London forces. So this is the trend. You keep this in mind, very, very important. If you know this, you can very easily answer. Very easily answer whatever question that comes to you, is given to you. Now listen, just I'll give you some examples so that you can easily understand what I'm trying to say. Right? Example number 1. Suppose I'll give you two liquids like this. Right? Say one is acetone, and another one is carbon disulfide. I am giving you two liquids A and B. The question is whether the two on mixing form ideal solution or non-ideal solution showing positive deviation or non-ideal solution showing negative deviation. How to answer this question? Students, very simple. See the two and find out in which one attraction is stronger. Okay, in carbon disulfide, it is a linear molecule. Carbon disulfide is a linear molecule, and there is no net dipole. Okay, dipole moment is 0, so it is a non-polar molecule. Students, keep this in mind. Carbon disulfide is a non-polar molecule, whereas acetone, listen here, we have carbon oxygen double bond. Oxygen is more electronegative, therefore you will get partial negative charge on oxygen and partial positive charge on carbon. Okay, you will get dipole. Pole means charge. You know very well, pole means charge. Dipole means two charges. Yes, I am getting a partial negative charge on oxygen and a partial positive charge on carbon. So I am getting a dipole. Now between acetone molecule, so this is a dipole, so here we will get dipole attraction. Here we will get dipole attraction. In carbon disulfide, it is non-polar molecule, so we have London forces. So in carbon disulfide we have only London forces, whereas in acetone we have dipole attraction. Which is stronger? Students, which one is stronger?
London force.
Dipole attraction is stronger, right? So the attraction in acetone is stronger. Okay, now what will happen if I put carbon disulfide in this. If I put carbon disulfide in this, right, carbon disulfide molecule will break. See, suppose this is one acetone molecule. Students, observe this carefully. I am drawing acetone molecule like this. Here we have partial positive charge, here we have partial negative charge, and I have another acetone molecule. I'll take another acetone molecule. Here we have partial positive, here we have partial negative. Listen, between negative end of one dipole and the positive end of another dipole, there is an attraction. There is an attraction between negative end of one dipole. This is a dipole, this is another dipole. Between negative end of one dipole and the positive end of another dipole, okay, there is an attraction. This attraction is what we call as dipole-dipole attraction. In pure acetone, if you take pure acetone, right, we have lot of dipole-dipole attraction, so strong attractive forces are there. But if I mix carbon disulfide, carbon disulfide is a non-polar molecule. What it will do? It will break these attractions, because carbon disulfide molecules will go in between acetone molecule, and the forces of attraction, right, starts to decrease. Whenever force of attraction decreases, we call the solution as, students, if force of attraction between AB, because this is non-polar, this is polar molecule, between these two there is no attraction is very weak. Okay, I can say it the other way. Listen, I'll give one more here. Dipole and non-polar molecule. Next one is London forces. Okay, it goes like this actually. So dipole-dipole attraction is stronger. In acetone, we have only dipole-dipole attraction. But when we mix carbon disulfide, okay, this attraction decreases and new attraction comes. What's the new attraction? Acetone and carbon disulfide attraction. Acetone is dipole. Carbon disulfide is non-polar. Dipole non-polar attraction is weaker than dipole-dipole attraction. Therefore, the force of attraction between AB is weak. Force of attraction between AB is weak. If the force of attraction between AB is weak, you will get positive deviation. Simple. So this solution will show, or if you mix acetone and carbon disulfide, I will get non-ideal solution showing positive deviation. No doubt. Is this clear, student? Any doubt in this? I'll give one more example so that you can easily understand. I'll give one more example. I'll take two liquids, say methanol and water. Methanol and water. Okay, students, observe this carefully. How to proceed? How to proceed if question given like this? Very simple. You see the two liquids. Among the two liquids, in which liquid force of attraction is stronger? That you have to decide. In this case, water molecule will show hydrogen bonding. Methanol also will show hydrogen bonding. Both will show hydrogen bonding now. But the hydrogen bonding attraction, since we have two hydrogen here, okay, in water oxygen is connected to two hydrogen, whereas in methanol oxygen is connected to one hydrogen and one methyl group. So here water molecule can form hydrogen bond with this hydrogen, with this oxygen, you will get two hydrogen bonds. So each molecule can form 4 hydrogen bonds, okay, in water, in liquid water. So the hydrogen bonding attraction is stronger here. Whereas in methanol molecule, this hydrogen can form hydrogen bond. These two oxygen can form 2 hydrogen bond, but methyl group cannot form hydrogen bond. Therefore, if you compare the total hydrogen bonding attraction in water is strong. Okay, it is more, it is less compared to water. Hydrogen bonding attraction is less here, because I have a methyl group here. That methyl group does not form any hydrogen bond with water, with the other molecule. Okay, so among these, which is stronger? Water, right? So in water molecule we have hydrogen bonding between one water molecule and another water molecule. There is an hydrogen bond. Okay, we have strong hydrogen bonds. But if you put methanol, students observe carefully. First you see the two liquid. In which liquid stronger force of attraction is there, take that. Then add the other liquid. If you add other liquid, what will happen? Listen, you will get a new force of attraction between water and methanol. But listen, since you have methyl group here, the extent of hydrogen bond formation, or the amount of hydrogen bond formation, I can say like this. Okay, amount or total number of hydrogen bond formation, okay, in the liquid will reduce. Yes, between water molecule and one water molecule, between two water molecule we have a hydrogen bond. Between water molecule and methanol molecule also we have hydrogen bond, no doubt in that. But due to the presence of this methyl group, this cannot form hydrogen bond with the other molecules. Therefore, the net force of attraction decreases. Is this clear, student? Whereas here, this water molecule can form hydrogen bond, this can form, right? Both these water molecule can form hydrogen bond with other water molecules. So in pure water, hydrogen bonding attraction is very, very strong. The moment you mix methanol, what will happen? You will get hydrogen bond between water and methanol. Okay, this hydrogen bond is okay, but since we have methyl group, this methanol molecule cannot form hydrogen bond with other water molecules. So the net force of attraction decreases. The net force of attraction decreases on mixing the two liquids. Right? Whenever force of attraction decreases, you will get positive deviation. So this mixing of methanol and water, right, will give positive deviation. Sometimes people will say this, whenever alcohol comes, students listen, whenever alcohol comes, you will get positive deviation. It's a trick. Okay, but we cannot follow the trick always strictly, right? But anyway, keep this in mind. Whenever alcohol comes, you will get positive deviation, right? Okay, good. Is this clear, student? Any doubt? So methanol water mixture, if you mix methanol and water and if you form a solution, that solution will show positive deviation. Okay. Then now I'll give few more examples for solution showing positive deviation. I'll just list out whatever examples, right, that you have to remember, right? So methanol and water will form positive deviation. Ethanol, okay, CH3 CH2 OH, ethanol and water form positive deviation. Then methanol and carbon tetrachloride, methanol and carbon tetrachloride form positive deviation. Then acetone and carbon disulfide, I gave this example, right, will form positive deviation. Then ethanol and cyclohexane. Okay, students listen, this molecule is called cyclohexane. Okay, if you mix cyclohexane with the ethanol, you will get positive deviation, right? Then acetone plus ethanol ethanol CH3, CH2, OH will give positive deviation. Many examples are there. Carbon tetrachloride plus toluene. Student, this is benzene. This molecule is cyclohexane. This molecule is benzene. In benzene, if I attach a methyl group, I'll get a compound called toluene. Toluene. Right? Toluene and carbon tetrachloride mixture will form positive deviation. Right? Then carbon tetrachloride and chloroform will give positive deviation. Then acetone CH3COCH3. This compound is called acetone. I have given already. Anyway, note down the name. Acetone, also called propanone. Propanone and benzene. Propanone and benzene form the positive deviation. Okay, these are all few examples for solution showing positive deviation. Then I'll give one more example. CH3COCH3 acetone plus ether. Okay, I'll take diethyl ether, O, dimethyl ether or diethyl ether, CH2, CH3, CH2, CH3. This is an ethyl group, this is an ethyl group, so it is called diethyl ether. Okay, acetone plus diethyl ether or any ether in general. Right? If you mix, you will get solution showing positive deviation. Okay, yeah, take down. All these are examples for solution showing. All these are examples for solution showing positive deviation. Positive deviation from Raoult's law. Okay, and here remember, among methanol and water, there is a strong force of attraction exists between water-water molecule. Okay, and if you add methanol, the force of attraction decreases. Similarly, among ethanol and water, force of attraction is strong in water. So if you add ethanol, force of attraction decreases. Okay, in methanol and carbon tetrachloride, in methanol we have hydrogen bonding attraction. CCl4 non-polar molecule. So if you add, okay, attraction decreases. In carbon disulfide we have dipole-dipole attraction. If you add, in acetone we have dipole-dipole attraction. If you add carbon disulfide, the attraction decreases. In ethanol we have hydrogen bonding. Cyclohexane is non-polar molecule. So if you add cyclohexane in ethanol, the hydrogen bonding attraction gets reduced, or the extent of attraction decreases. Okay, then here we have acetone, we have ethanol. In ethanol we have hydrogen bonding. Hydrogen bonding attraction is stronger. In acetone we have dipole-dipole attraction. Okay, but if you mix acetone in ethanol, right, the extent of hydrogen bonding attraction decreases. So force of attraction decreases. That's why it shows positive deviation. Carbon tetrachloride toluene, these are all some special cases. Carbon tetrachloride and toluene. Here carbon tetrachloride is perfectly nonpolar molecule, perfectly nonpolar. But in toluene there is an pi-pi attraction, right? Here we have pi electrons. In other toluene molecule also we have pi electrons. So there will be some kind of pi-pi attraction will be there. But if you add CCl4, those attraction decreases. Okay, so on average the attraction decreases. Students, turn on your camera, everyone. Turn on your camera. Okay, so it's a special example, student, keep this in mind. Often if you go to competitive examination, they'll ask questions like this, right? CCl4 toluene, if you mix, you will get solution showing positive deviation. Okay, CCl4 and chloroform. In chloroform we have dipole-dipole attraction. Okay, if you CCl4 is non-polar molecule, so if you add CCl4 in chloroform, force of attraction decreases. Okay, similarly here, as in acetone we have dipole-dipole attraction. If you add benzene, right, in acetone, the dipole-dipole attraction gets reduced. Right? Here also in acetone we have dipole-dipole attraction. If you add ether, the dipole-dipole attraction gets reduced. Whenever force of attraction reduces, you will get solution with the positive deviation, non-ideal solution with showing positive deviation. Okay, is this clear, student? Any doubt? Any doubt? Note down all these examples. Okay, and keep this in mind. In general, whenever alcohol comes, see, ethanol, alcohol, whenever alcohol comes, okay, you can say that the solution is positive, so shows positive deviation, right? It's a simple trick we often use, but we have other examples also. So here, this example number 7, example number 8, okay, these are all some important examples. You can expect these questions in the competitive examinations. Okay, now, so for solution showing for non-ideal solution, showing positive deviation, okay, these are all the points you should remember. Number 1, I'll just summarize the point. Number 1, force of attraction between AB after mixing, okay, force of attraction between AB is less compared to the force of attraction between AA, right, or force of attraction between BB. It is weak. Number 2, observed total pressure, okay, is greater than the calculated total pressure. Number 3, delta V mixing is positive. Positive deviation, positive. Okay, delta V mixing positive. Delta H mixing also positive. Okay, remember students, these two you can answer easily. If the solution is positive, if the solution shows positive deviation, these two should be positive. If the solution shows negative deviation, these two should be negative. Simple. If the solution is ideal solution, in that case both are 0. Okay, we have seen this in the last class, right? Then number 5, delta S mixing. Delta S mixing is positive. Number 6, delta G mixing is negative. Delta G mixing is negative, right? And I have given an information here, T into delta S mixing, okay, should be greater than delta H mixing for solution showing positive deviation from Raoult's law. Okay, note down all these things. All are very, very, very important. These are all characteristic informations on solution, non-ideal solution showing positive deviation. Then I'll give another important point here. If I plot vapor pressure, right, in y-axis, I'll plot vapor pressure in y-axis, vapor pressure, and percentage composition in the x-axis. Okay, see what I'm trying to do is I'm going to plot mole fraction of B in x-axis. So here mole fraction of B is 0, here mole fraction of B is 1. You know very well, for mole fraction lowest possible value is 0, highest possible value is 1. Students, keep this in mind. For mole fraction, lowest possible value is 0, highest possible value is 1. Okay, listen, if mole fraction of B is 0 here, which means we have only liquid A. We have only liquid A. Here mole fraction of B is 1, which means we have only liquid B. So here we have pure liquid A. At 0 we have pure liquid A. At 1 we have pure liquid B. That's the meaning. Okay. Let us suppose P naught A, P naught B. Students, what are these? What are these quantities? P naught A, P naught B. What is P naught A? What is P naught B? This not symbol indicate pure. Yeah, switch on your mic. Okay, listen. P naught A means vapor pressure of pure liquid A. P naught B means vapor pressure of pure liquid B. Now let us assume that P naught B is greater. It's an assumption, suppose. Okay, then see, here I have pure liquid A, here I have pure liquid B. Vapor pressure of pure B is greater, so this is greater and A is smaller. A is smaller compared to that. Compared to this is vapor pressure of pure B. This is vapor pressure of pure A. I am assuming like that. It is less, right? And if you add liquid B in pure, see, I have pure A. In pure liquid A, I am adding liquid B. If you add liquid B, what will happen? Mole fraction of B starts to increase. If it increases, students, observe carefully. If it is an ideal solution, I will get a straight line, which we discussed in the last class. If it is an ideal solution, we should get a straight line. But now your solution shows positive deviation. Correct? In that case, you know very well, this is calculated total pressure. Students, this dotted line indicate calculated total pressure at various composition. But you know very well, for solution showing positive deviation, observed pressure, experimental pressure is greater than the calculated. Therefore, the vapor pressure curve, okay, for solution showing positive deviation will go like this. Will go above this line. Okay. Then this curve, let me draw here. This line corresponds to here. See, on adding B, vapor pressure of A decreases. So this is vapor pressure of A, and this one corresponds to vapor pressure, partial vapor pressure of B. Right? On adding B from left to right, okay, mole fraction of B increases. Correct? That means we are adding liquid B. When you add more and more liquid B, mole fraction increases. When you add more B, partial pressure of A will decrease, partial pressure of B will increase. But this dotted line corresponds to ideal solution. But for non-ideal solution, students, remember, this is very important. For non-ideal solution showing positive deviation, I wrote shortly like this. Okay, now Ni means non-ideal solution showing positive deviation. I have told you total observed pressure is greater than the total calculated. Yes, I have shown here. This is calculated and this is the observed pressure. Not only that, partial vapor pressure of A, students, partial vapor pressure of A, which is obtained through experiment, it is greater than the product of these two. and you know very well, this is obtained from Raoult's law. Okay, this will give you partial pressure of A, okay, through Raoult's law. This is partial pressure of A actually exists in the solution, experimental. So students are able to follow this. P naught A into XA is the partial pressure of A calculated using Raoult's law, whereas this is partial pressure actually present in solution, and the actual partial pressure is greater than the partial pressure of A calculated through using Raoult's law. Similarly, partial pressure of B also greater than P naught B into XB. Okay, not only this, that's the point I'd like to say. Not only this, even partial pressure of A is greater than this, partial pressure of B is greater than this, because solution shows positive deviation, right? In solution showing positive deviation, these values are greater than that. Therefore, here also, so if you plot for partial pressure of A, you will never get a straight line. The straight line is possible only for ideal solution. Since your solution showing positive deviation, the actual partial pressure is greater than this. Okay, this is partial pressure calculated through Raoult's law. If you calculate through Raoult's law, I will get a straight line like this. Similarly, this is calculated through Raoult's law, partial pressure of B, but the actual partial pressure of A is greater than the partial pressure of A calculated using Raoult's law. Therefore, here also the curve will go above this line. Here also the curve go above this line. So you will get, students observe carefully, that dotted line corresponds to ideal solution. But now your solution is non-ideal, showing positive deviation. Whenever positive deviation is given, the curves will go above ideal straight lines. Positive deviation means the curve will go above the straight line. That's the point. Okay, and this curve is called vapor pressure composition curve. Vapor pressure, we call mole fraction simply as, you can say mole fraction simply as composition. So this diagram is called, or this graph is called, okay, vapor pressure composition diagram. Note down. In vapor pressure composition diagram, if you get curves above ideal straight line, okay, say this is a straight line for ideal solution. If you get curve above this, we call the solution as solution showing positive deviation. Now I am going to give you another important point here. For the same solution, now I am going to plot. Students observe carefully. Now I am going to plot boiling point. Okay, boiling point versus composition. Boiling point versus composition. So here also mole fraction increases. Students observe this carefully. Now I'm not plotting vapor pressure. I'm plotting boiling point. Remember, boiling point. Okay, just for understanding purpose, I'm giving this understanding purpose. Boiling point is inversely proportional to vapor pressure. What is meant by that? If vapor pressure is high, students, if vapor pressure is high,
boiling point is less.
okay, if vapor pressure is, yes, you're right. If vapor pressure is high, boiling point will be low. Okay, now listen, see here, among A and B, which vapor pressure is high? A or B?
B is
Vapor pressure of B is high, right? Therefore, if you take boiling point of B will come down, boiling point of A will go up, correct? Because boiling point is inversely proportional to vapor pressure. Therefore, boiling point of B will come down. So this is boiling point of, okay, T naught B in border. T naught B means boiling point of pure liquid B. and T naught A is boiling point of pure liquid A. You'll get just opposite to that, and straight line corresponds to ideal solution. The straight line corresponds to ideal solution. Okay. Now if I plot boiling point at different composition, if you plot boiling point at different composition, the boiling point curve will go like this. Is it below straight line or above straight line? So listen carefully. Below straight line means don't think that it is negative deviation. Here we are plotting boiling point versus composition, correct? So if you want to say whether a solution is positive deviation or negative deviation using just a diagram, you have to see vapor pressure composition diagram. In vapor pressure composition diagram, if the curve goes above the straight line, it is positive deviation. Whereas in boiling point composition diagram, students, be careful in this. If boiling point composition diagram is given, you should be little careful. Here the curve goes below straight line, but this solution is a solution showing non-ideal solution showing positive deviation. So it is very, very important which diagram that you are seeing. If it is a vapor pressure composition diagram, if the curve goes above straight line, it is positive deviation. If it is boiling point composition diagram, if the curve goes below straight line, then it is positive deviation. And see here, at one particular composition, students, at one particular composition, you'll get the lowest boiling point, right? You'll get a lowest boiling point at one particular composition, right? This composition or this temperature, the lowest temperature that is possible here, this temperature is called okay, this is the lowest, this temperature is lowest possible temperature, and this composition is called azeotropic mixture. A-Z-E-O, azeotropic mixture. Azeotropic mixture. Solution showing positive deviation, okay, will give low boiling azeotropic. See, among the other composition, right, this is the lowest possible boiling point. Okay, you'll get low boiling azeotropic mixture, right? Non-ideal solution showing positive deviation will give low boiling azeotropic mixture. Okay, what is azeotropic mixture? What is azeotropic mixture? Very simple. Let me give this a point and I stop. Students, what is meant by azeotropic mixture? Suppose I'll take a container and I'll take a solution containing A and B. Just for understanding purpose, I'm saying this. Just for understanding purpose. Heat the solution. Okay, vapors will come out. Right? You have the A and B vapors. Okay, students, observe carefully. Suppose if the percentage of A and percentage of B in the liquid, say for example, percentage of A is 40, percentage of B is 60 in the liquid. Then you measure the percentage of A and B in the vapor state. Percentage of A, percentage of B in the vapor state. If the percentage of A and B is again the same, students, the percentage composition in the liquid phase and the percentage composition in the vapor phase are same at boiling. Okay, assume that now the solution is boiling at the boiling point, right? At the boiling point, if the percentage composition in the liquid phase and the percentage composition in the vapor phase are same, okay, we call that solution as azeotropic mixture, because an azeotropic mixture is one in which the composition in the liquid phase and the composition in the vapor phase are same at the boiling point. Therefore, you cannot separate A and B by simple distillation, because the composition remains same in the liquid phase as well as in the vapor phase are same. Okay, the compositions are same. Therefore, you cannot separate A and B by simple distillation. Okay, in case of azeotropic mixture, right? In azeotropic mixtures, right? Azeotropic mixture cannot be separated. Separated by simple distillation technique. Why? Because if you make simple distillation, then the composition in the liquid phase and the composition in the vapor phase remains same at the boiling point. It remains same. If the composition in the vapor phase and liquid phase remains same, then you cannot separate A and B. Right? You cannot separate A and B. That's the point. Right? So azeotropic mixture is a constant boiling mixture. You can say in the other way. Azeotropic mixture is also called as constant boiling mixture. What is meant by constant here, student? Azeotropic mixture is a constant boiling mixture. What is meant by that? Why we are saying constant?
Composition in solid and liquid phase.
Switch on your mic, ma. Switch on your mic.
So my video is on.
I'm not audible. Aditi?
Sir, my video
yeah.
is on. Can you hear me?
What is the meaning for constant here?
Same composition in liquid and gas phase.
Very good. Very good. Listen, if the composition is same in the liquid phase and the vapor phase at the boiling point, that's the point. If the composition is same, then you cannot separate A and B. That is why we are saying that it is constant boiling mixture. So what is azeotropic mixture? Azeotropic mixture is a constant boiling mixture. What is the meaning for constant here? Meaning is the composition in the liquid phase and the composition in the vapor phase are same at the boiling point. That's the meaning. Okay? Is it clear, student? Yeah. Okay, I stop here. So we discussed non-ideal solution showing positive deviation. Okay, I'll give 1 or 2 examples for azeotropic mixture in the next class. Then we'll discuss non-ideal solution showing negative deviation. As we have spent a lot of time in positive deviation, okay, negative deviation I'll just rush up. Okay.